PN junction diode. If one side of a single crystal of pure semiconductor like germanium or silicon is doped with acceptor impurity atoms and other side is doped with donor impurity atoms, a PN junction is formed as shown in figure. P region has a high concentration of holes and N region contains a large number of electrons. PN junction formation. Consider a thin P-type silicon semiconductor wafer. By adding precisely a small quantity of pentavalent impurity part the P silicon, that means P-type silicon wafer can be converted into N-type silicon. The wafer now contains P region and N region and a metallurgical junction between P region and N region. Two important processes occur during the formation of PN junction, that is diffusion and drift. We know that in an N-type semiconductor, the concentration of electron is more compared to the concentration of holes. Similarly, in P-type semiconductor, the concentration of hole is more than the concentration of electrons. During the formation of PN junction and due to the concentration gradient across P and N sides, holes diffuse from P side to N side, P to N, and electron diffuse from N side to P side, N to P. This motion of charge carriers gives rise to diffusion current across the junction, as you can see in this diagram. When an electron diffuses from N to P, it leaves behind an ionized donor on N side. This ionized donor positive charge is immobile as it is bonded the surrounding atoms. As the electron continue to diffuse from N to P, a layer of positive charge on N side of the junction is developed. Similarly, when a hole diffuses from P to N, due to the concentration gradient, it leaves behind an ionized acceptor, negative charge, which is immobile. As the holes continue to diffuse, a layer of negative charge on the P side of the junction is developed. This space charge region on either side of the junction together is known as depletion region, as the electrons and holes taking part in the initial moment across the junction depleted the region of its free charges, as you can see in this diagram. The thickness of depletion region is of the order of 1/10 of a micrometer. Due to the positive space charge region on N side, the junction and negative space charge region on P side of the junction, an electric field directed from positive charge towards negative charge develops. Due to this field, an electron on P side of the junction moves to N side and a hole on N side of the junction moves to P side. The motion of charge carriers due to the electric field is called drift. Thus, a drift current which is opposite in the direction of diffusion current starts, as you can see in this diagram. Initially, diffuse current is large and drift current is small. As the diffusion process continues, the space charge region on either side of the junction extend, thus increasing the electric field strength and hence drift current. This process continues until the diffusion current equals to drift current. Thus, a PN junction is formed. In a PN junction, under equilibrium, there is no net current. The loss of electrons from the N region and gain of electron by the P region causes a difference of potential across the junction of the two regions. The polarity of this potential is such as to oppose further flow of carriers so that a condition of equilibrium exists. Figure shows the PN junction at equilibrium and the potential across the junction. The N material has lost electrons and P material has acquired electrons. The N material is thus positive relative to the P material. Since this potential tends to prevent the movement of electrons from the N region into the P region, it is often called a barrier potential, as you can see in this diagram.